नमस्कार।
हो गया अंदर
Namaskar and a very good afternoon to one and all. Respected Secretary, Department of Health Research and Director General, Indian Council of Medical Research, Padma Shri Professor Balram Bhargav, Honorable Chief Guest, Padma Shri Professor K. Vijayaraghavan, Professor P.P. Talwar, Director ICMR-NIMS, Dr. M. Vishnuvardhan Rao, Head of Divisions of ICMR, Dr. Padam Singh, former Director ICMR-NIMS, and additional DG of ICMR, Senior FA, Heads of Division of ICMR, Directors, Ex-Directors, Scientists from ICMR Institutes, and other distinguished guests. who are participating today in person and through virtual platform. I'm extremely privileged and honored to extend a warm and hearty welcome to one and all on behalf of Director and staff of ICMR-National Institute of Medical Statistics to the 5th PP Talwar Oration Awards. This oration was established in the year 2015 to promote evaluation research in public health programs. We start the proceedings with a prayer. I request my colleague and senior scientist Dr. Tulsi Adhikari and team to render the Saraswati Vandana. Shri Anil Lakheda, ICMR, will accompany the singers on the Basuri.
मन से हमारे मिटागे अंधेरे, मन से हमारे मिटागे अंधेरे, हमको उजालों का संसार दे माँ, हे शारदे 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 माँ।
Thank you for the beautiful rendition. Now I request Director ICMR-NIMS to deliver the welcome address.
Thank you. Respected Chief Guest, Dr. P. Vijayaraghavan, distinguished professor and renowned biologist, currently the Principal Scientific Advisor, Government of India, our beloved Director General and Secretary DHR, Professor Balram Bhargav, colleagues from the ICMR fraternity, my colleague directors who are online and who are joining virtually today, I deem it my great pleasure to welcome you all. I am sure all of you in this hall today and those participating virtually can already see the auras spread by these two highly learned men. 100 years, we have been the pillars of science, technology, biology, and medical research in the country. They are the examples of humility, exemplifying the ancient Indian dictum, Vidya Dadati Vinayam, Vinaya Dayati Patratam, which roughly translates to great education gives great humility, and with the great humility comes great character. On behalf of the fraternity of ICMR, and most importantly, on behalf of the National Institute of Medical Statistics, I welcome you both, sir, for this important event. Professor P.P. Talwar an eminent biostatistician and demographer who earlier served as a head and professor in the Department of Medical Statistics, NIHFW, New Delhi, and a friend and well-wisher of ICMR-NIMS, had instituted Professor P.P. Talwar Oration Award in the year 2015 with the objective of highlighting the importance of program evaluation in the country. The award is being conferred to eminent personalities who have contributed significantly to human development through their exemplary medical, scientific, and research work. The previous orations were delivered by Professor M.K. Bhan, former Secretary DBT, Dr. M.S. Swaminathan, renowned agriculture scientist, Dr. N.K. Ganguly, former Director General of ICMR, Professor V.K. Paul, member Niti Aayog. The fifth Professor P.P. Talwar oration today being delivered by Professor K. Vijayaraghavan, entitled Big Data and Big Ideas in Discovery and Application in the Life Sciences. We are elated to see the title, as our DG ICMR is keen in strengthening the big data and artificial intelligence in ICMR, and created a cell exclusively for this to work on to strengthen these activities. The title is very apt in the current situation, as huge data is being generated by organizations, and also data is a new oil now. We are shifting from hypothesis-driven research to data-driven research. It is also coincides the 46th Foundation Day of ICMR NIMS on 26 September 1976. The then Union Minister of Health and Family Welfare, Dr. Karan Singh, laid the foundation stone. I am heading an institute where people like statistics, people hate statistics, people dislike statistics, but everyone wants statistics. In the advent of freely available open source statistical software, Google-like search engines, a lot of researchers using those without knowing the theory behind that, which may result in erroneous interpretations. According to Professor R.A. Fisher, who is the father of statistics, to consult the statistician after an experiment is finished is often merely to ask him to conduct a post-mortem examination. He can perhaps say what the experiment died of. Therefore, I suggest my scientists in NIMS that not only they should apply statistics effectively, but also see that it is not misused. Hence, a lot of dissemination of subject of statistics is the need of the hour. We are thankful to Professor Vijayaraghavan for accepting to deliver this year oration, and our DG ICMR for constantly supporting and guiding us. We will strive to live up to your expectations, sir, and the nation's expectations. I will have to acknowledge all the help provided by my colleagues and ICMR in organizing this important event. Before that, I have a request to our chairman, sir. Actually, our scientists have prepared a small AV on NIMS. If you permit, we can play for 2 minutes. Okay.
I think at the end before.
Okay. So, good evening and namaskar. Thank you very much.
Thank you, sir. Before I request Professor P.P. Talwar to address the august audience, I take this opportunity to introduce him. Professor Prem P. Talwar, a biostatistician and demographer by training, is the former head, Department of Statistics and Demography, National Institute of Health and Family Welfare, and has over 5 decades of experience in social science research. Professor Talwar served as the chairman, Social Division of the GFK Mode Services, where his role was to evaluate various social developmental programs in the country. He had also been a member of the International Advisory Committee of the Asian Urban Information Center of Kobe, Japan. Professor Talwar has published over 100 papers in national, international, peer-reviewed journals and books. His areas of interest are monitoring and evaluation research in social programs with emphasis in health and family welfare. I thank you, sir. So please deliver your address and tell us about the institution of the award.
Thank you. Honorable dignitaries on the dais and my fellow colleagues here, I'm here to give you a short background of this oration. I think Dr. Rao already has indicated quite a bit about the speakers, etc. My task is only to give you a short description. I I've been a student of changing Indian demography and health scenario in the country, and for quite a few years I've been working on it. I've seen a generally slow decline in our health indicators have always concerned me and made me to think for the reasons. I attribute this slow process in either ignoring or non-seriousness use of two significantly important components of the program. One is monitoring, the other is evaluation, which broadly we can call programmatic research as a general term. I always felt that implementation of these two components in our health program has been inadequate because of poor understanding of their role in making a program effective. While monitoring helps in fine-tuning the program and the strategy, the evaluation provides leads as to which components of the program are useful and helpful in improving health of the people and which components need to be modified or even replaced. We never try to undertake enough program-related researches so as to ensure that the program works at its optimum level. I strongly feel and believe, and existing literature supports the fact that a good monitoring and evaluation could improve output of the outcome of the program by at least 25%. This is what literature says. The approach I took to strengthen these two components of the program was through advocacy of these two components. I wanted that more and more people should talk about and realize it. These two components, monitoring and evaluation, are program researches. This is what was in my mind when I discussed in 2014 the possibility of instituting an Oration Award with the then director, Dr. Arvind Pandey of the National Institute of Medical Statistics, and directly and indirectly with Dr. B.M. Katoch, the then DG ICMR, the Secretary Health, Government of India. I wanted an oration on the role and importance of monitoring and evaluation on serious program research to hammer the importance of these two components of the health program. I was happy that the response of National Institute of Medical Statistics and ICMR was positive, and I feel indebted to them for agreeing with my proposal for instituting Oration on this neglected but very important component of the program. Now, I am very happy that for this fifth Oration, Dr. Rao, Vishnu Rao, the current Director of Energy, and with the blessings of the present Director General ICMR, Professor Balram Bhargava, could motivate and persuade an eminent person like Dr. A. Vijayaraghavan, Principal Scientific Advisor to Government of India, to spare time and be with us today for the Oration. His vast experience with research, applied research, some people call applied research, some people call program research, and research community will be very useful to convince the researchers on the need for good research in strengthening the program. His voice, I'm sure, will be able to make a strong pitch for strengthening research and influence components of the program, which is partly his topic today, which I feel are very important for making program more effective and result-oriented. Again, in the end, I'd like to thank the ICMR and the Dr. Rao for really conducting this oration today and being able to invite the learned person like me. Thank you very much.
Thank you, sir, for giving us the valuable insight. I request respected Secretary DHR and DG ICMR, who is presiding over the program, to kindly address the elite audience.
Thank you so much. So, dignitaries on the dais and luminaries in the audience, it is my pleasure to welcome you all to this fifth Professor P.P. Talwar Oration being organized by National Institute of Medical Statistics, celebrating its 46th anniversary. It was conceived and set up in 1976, and since then it has been supporting the data research for the country in every which way. I congratulate the director and the previous directors who are all present today, Dr. Odam Singh, Dr. Pandey, and he's online, and Dr. Shukla. So I thank you all for supporting Indian data research for decades to come, for the decades in the past. Most importantly, I'm delighted that we have one of the finest speakers today and one of the best orators who will be giving this oration, Professor K. Vijayaraghavan, who is the Principal Scientific Advisor to the Government of India, and is a Fellow of the Royal Society, as well as several other societies, and has received several awards. I will not name all of them because it is just including the Firodia Award, the JC Bose Award, the Infosys Award, and other awards. So I will not stand between him and you, and the academic feast is about to start. Wish you all the best.
Thank you so much, sir, for the continued support. Before I request Honorable Guest of the Day, Professor K. Vijayaraghavan, to deliver the Professor P.P. Talwar oration on big data and big ideas in discovery and application in the life sciences, I'm privileged to introduce Professor Vijayaraghavan. Dr. Krishnaswamy Vijayaraghavan is a distinguished professor and a renowned biologist. Currently, he serves as the Principal Scientific Advisor to the Government of India and is the Chairperson of Prime Minister's Science, Technology and Innovation Advisory Council. He is a key advisor to the Government of Scientific Policy, Strategy and Innovations. He has also served as the Secretary of the Department of Biotechnology from 2013 to 2018. Professor Vijayaraghavan is an emeritus professor of the Tata Institute of Fundamental Research and former director of the National Center for Biological Sciences of TIFR, Bengaluru. He has made significant contributions in the field of developmental biology, genetics, neurogenetics, and neuromuscular systems. A new species of gecko, Hemidictylus Vijayaraghavani, I hope I've pronounced it properly, was named after him in 2018. Professor Vijayaraghavan is a recipient of several prestigious awards such as H.K. Firodia Award, J.C. Bose Fellowship, the Infosys Prize in Life Sciences, and the Bhatnagar Award. He was conferred upon the Padma Shri in 2013 by the Government of India. May we have a big round of applause for Padma Shri Dr. K. Vijayaraghavan. I now request Professor Dr. Vijayaraghavan to kindly deliver the oration. Thank you, sir.
Okay. Good evening, everybody. Dr. Vishnuvardhan Rao, Professor P.P. Talwar, to whom we are all very grateful for instituting this lecture series. Professor Dr. Balram Bhargav, Secretary DHR and Director General ICMR, and all my colleagues over here, Dr. Padam Singh and everyone else in this room, as well as those online. It's a great honor, of course, to give this lecture, but I do so with much trepidation because I'm in the National Institute of Medical Statistics, and this is a place where data can be best analyzed and studied. And I'm here to talk about the role of big data today in biology. Now, this is, of course, a big challenge, and the challenge comes from two kinds of situations. One, the increasing ease of collecting data has been there for some time, but now computational power using algorithms which were put in place many, many years ago, and the ability to store data, retrieve it, and compute with speed using these algorithms has resulted in the growth of artificial intelligence and machine learning. And that allows us to analyze data at different time points and then use that to predict what the next time point will be, and also learn and make predictions about the provenance and the impact of data when we see it in new context. Now, this does not mean that we will not have any more requirement for deep domain understanding. Quite the opposite. The data alone is completely insufficient for our understanding and decision making. And not having data is not the solution to have just domain understanding without data. Both are needed, and which is what I'll try and illustrate now. Now, this picture which you see is of the telescope in Hanle in Ladakh. And I put this up here to illustrate how astronomy was perhaps our first big data study. Earliest humans gazed up at the skies and saw stars shining without having to worry about city lights. And they drew all sorts of conclusions about it. But the most astute amongst them looked at not just the stars with awe, but found out that there were some planets whose movements they could study and understand. They could study and understand the movement of the sun and the moon, predict eclipses, and predict, seasons and so on and so forth. Later, stars were used for navigation and commercial activities in extraordinary ways. And much of this came along with this expansion of the study of astronomy. So here is an example of how one could have looked at all the data with great granularity, but our ancestors were actually more like detectives who picked from this data what was important and found what conclusions to take. Of course, this took, decades, centuries, millennia, and the speed of research and understanding is much faster now. Now, let us look at what our world will look like in, let's say, 2050. Now, if you ask economists, they will talk about emerging economies and how they will be, and how some countries such as India and China and Indonesia will grow and other countries will be balanced and so on. But if you ask people who are interested in the state of the planet, the health of the planet, they will talk very worryingly about climate change, biodiversity, the environment, sustainable livelihoods, and so on. So how have we come about to such a state where we need to worry about whether the planet is safe in 2050 or not? Now, one of the kinds of directions which we will take going ahead is going to be the preponderance of data about big data and its analysis. And we will have to bring this into consideration as we go into the future. But the important point going ahead to the future is that all of this is combined with a great need to do something about the areas I mentioned: climate change, health, agriculture, and so on and so forth, in a manner which brings us back from the precipice the planet right now is. Extreme weather events, rising sea levels, altered biodiversity, all pose great threats which we need to address going forward. Now, so we have a big manthan, as it were, and this is about big data and big ideas in discovery and application in the life sciences. But this is true of all areas which we can see going ahead. And this manthan has come about for through two kinds of trajectories. One is the evolution of us as humans themselves. And that has happened by accident upon accident during evolutionary history. And we have got enormous capabilities because we can oppose our thumb and forefinger. We can speak. Language is a great ability, and processing of speech in the brain. And importantly, we have a disproportionately large brain compared to our body size when compared to other non-human, when compared to non-human primates, which gives us extraordinary computational power. With all of this, we have moved away from merely being selected evolutionarily for survival on the planet to becoming those who have actually become stewards of the planet. In other words, we have moved from being survivors on the planet of the apes to creating what I would call the planet of the apps. Now, through this, we have to look at what we are doing in another front. I mean, through the industrial revolutions, we have changed the planet in many ways. We've changed our lives as humans in many ways. But we've also developed data computing, and this needs to be examined in terms of asymmetry of powers that this creates and what happens to society. How did this come about? Now, when we look at that, we ask, what is this term artificial intelligence and what it means and how it'll have a great impact on life sciences. So the key question about artificial intelligence is simple: can machines think? And Alan Turing asked this in 1950, and he put this out in a very brief paper, which has, I think, just 2 references and is very beautifully articulated. And here is Alan Turing, running. He was at Bletchley in the Second World War, breaking the Nazi code, and he used to often run from there to Cambridge for intellectual stimulus or to London to meet his bureaucratic bosses. But he was not only involved in deciphering the Nazi code, but he was also very key in asking this question about whether machines can think. And he developed the Turing test, which is, to put it very simplistically, is to ask if anyone of us here is actually a computer who's so good at being a human that we cannot distinguish that computer from a human. So if you pass the Turing test, you've created a computer which has not artificial intelligence, but general intelligence. So general intelligence is difficult to get, but narrow AI, which is also machine learning and deep learning, is something which is what we're seeing around us. And this was pioneered by Lovelace, shown here with the Babbage computer, and these kinds of computational tools developed very rapidly, but then hit a wall because of the problems with computational power and storage. Now that changed dramatically. Now, what is narrow AI? Shown here is a picture at the top of an early stage termite hill under construction, and then later on a full termite hill on the campus of the University of Agricultural Sciences in Bangalore. Now this termite hill, if you open it, has got an extraordinary system of air conditioning, and it's got extraordinary chambers going deep down and wide under the underground. Now, how does this organization come about? Is there a central command putting all this in place? There isn't. Every single termite who's working over here interacts with her neighbor, and depending on the context, does something. And this context-dependent interaction results in an extraordinary structure where everyone has got competence, but no one has got comprehension. So this is an example of how all of this can be potentially mimicked by a computer, and it can theoretically, we can program it to construct this in a similar manner in theory. We need to know a lot about the biology, but just as the termite hill has competence without comprehension, the computer also will have competence without comprehension. Now, what is, there are even more complicated aspects, and this, I will not show you this movie. This is a movie of a deer which is going to be chased by a cheetah. That the cheetah now, while it chases the deer, needs to not only know what is happening, but anticipate what can happen. And therefore, it learns through experience how to program its brain and its movement and its spinal cord in a manner to capture this deer, even though it doesn't know specifically what's going to happen in that situation. That too is today doable by computers. And therefore, these are all examples of machine learning and deep learning imitating natural systems, but these are not examples of comprehension. Now, what about artificial general intelligence? And that requires, a capability to be much more than this, narrow AI. That requires us to not only anticipate events, but to speculate, to have abstractions, to, in other words, to behave like humans with very sparse data. Humans have this extraordinary ability to do that, which even the best computers today don't have. But there are two schools of thought. One which says that eventually artificial general intelligence will be feasible through computers, and the other which believe that human consciousness, human abilities are unique and therefore are not in the near future imitable by machines. The artificial general intelligence, as I told you, you would require at the least to pass the Turing test. Now let us look at big data. Now today, whether you go to astronomy or medicine or the stock market, there is the ability to collect data at extraordinary granularity. You can collect data about where everyone's walking, which car is going around. You can collect data, inside a person's brain, inside a person's cell in that brain, and so on and so forth. So big data is everywhere. But we must remember that data is not information. And this rapid collection of data without annotation, even though there are machines which now can do substantial annotation, is throwing away a lot of information. So the collection of data and its annotation needs to be done in a manner which it generates information. And that information is what is necessary for knowledge as a primary level. So just raw data is not necessary. You have to convert that into information. Now, information itself is not knowledge, right? You might have very good annotated information of all the cars going around outside Ames. You might even know their car numbers, how they come and how they move. But if you want to analyze traffic, you need to convert this information into knowledge. And that knowledge is a much more complicated aspect. That knowledge requires you to have some domain understanding of transport, movement, and so on and so forth, how cars function, how buses function, and how this happens elsewhere in the world. Then this information becomes knowledge. But even that is not enough. You need now an understanding. And now you start going into domains which get more and more difficult. I show a picture of from a gamma ray observatory where you get a lot of information that's converted to knowledge, but it requires a good astronomer to be able to use all their experience and then make somewhat of a leap of faith, right? Saying that, look, I've got all this information. My computer will say these are the likely possibilities, but my computer very likely will tell me what the possibilities are according to the data it has interpreted and extrapolated from that. That is not going to be sufficient for reasoned action. So understanding is necessary, but now you make a leap towards general, AI, because that is not sufficient for reasoned action. So information is necessary for knowledge. Knowledge is necessary for understanding, and understanding is necessary for reasoned action. This picture shows Jocelyn Bell, who was looking at the data on a radio telescope and proposed what were known as pulsars later on. Most other people who are experienced with that data, they saw this information as being noise. And so she, because of her experience and understanding, said, this is not noise, this is something else, right? For which her supervisor, Anthony Hewish, got the Nobel Prize. She was left out, but Jocelyn Bell Burnell now is a famous astronomer. And this was a very important leap of faith that she made from her understanding. So now let's look at big data from human perspective. We can collect data, as I said, from transport around us or from what's happening in the cell, but we can also create data. And this picture shows data being created at the CERN reactor in Geneva, where you can generate big data in high energy physics of all kinds, make predictions by theory, and look at this generated data for validation of the theory. So you can also create the big data. And then on the right is shown the Chandrayaan launch, where again, big data is analyzed from space and from satellites being launched, from rockets being launched to take decisions on what's happening. Now let us go from all of this to intelligence. You have this ability computationally to collect data, analyze it, and reach conclusions. And you also have the ability, without having comprehension, but competence to create extraordinary structures, such as the termite hill. On the right of your screen, you have the city of Barcelona, where the architect Gaudi has created these enormous cathedrals which look like a termite hill. But that is not without comprehension. That's got a central command, which has ruthlessly executed the construction of a structure, directing workers to do specific things. It's not that the workers automatically knew what they wanted to do by chemical interactions with their neighbors, like in the termite hill. So this resulted in the kinds of cathedrals we see. That is intelligence, and that's what has been used by human societies in different ways, for good and for bad. Now, let us look in that situation to our origins, and I'll start, winding down over here. Now, as I said, our origins as humans had unusual evolutionary luck, but through that, we have understood not only how we came about, but we've understood nature's engineering, but we've also become engineers of nature. The Earth arose about 4.5 billion years ago, and about 1 billion years later, life originated on Earth. And we don't know how it originated, but we know that it's very likely to have all life on Earth today has a common origin. And that common origin also means that we have a shared chemistry with all life, and that shared chemistry is connected through a thread of DNA. And therefore, by looking at any organism, you can understand aspects of every other organism. And this is very, very important. And a lot of the discoveries which are useful in agriculture, in medicine, have come from the study of other organisms, model organisms in the lab, other organisms, microorganisms, biochemistry from all sorts of locations and so on. So the shared chemistry is critical. And we often, when we practice all the solutions which come from these kinds of biology and physics and chemistry, we forget their origins. So all of that in agriculture and medicine is anchored on fundamental research in mathematics, physics, chemistry, and biology. How did we come about? Well, here is a dinosaur named after Rabindranath Tagore, actually, which is in the Indian Statistical Institute in Kolkata. And this dinosaur is, was around the Earth about more than 65 million years ago. 65 million years ago, an accident happened, and such accidents can happen again today. An asteroid struck the planet, likely in Mexico. That created huge temperature changes and dust clouds, people hypothesize, and maybe other factors were involved, and dinosaurs became extinct. That allowed mammals, which were, playing around at the feet of the dinosaurs at that time, the mammalian radiation to expand and grow. And, over a period of time, here we are. So it's, the accident of an asteroid which resulted in us being here on this Earth, and maybe we never would have been otherwise. Now, all of our understanding of how we came about in relationship to other lives forms on Earth come from the work of Charles Darwin and Alfred Russel Wallace. And they, in my view, just like the astronomers earlier, were amongst the first big data scientists. Darwin went all over the world. Alfred Russel Wallace went to the Malayan archipelago, and they just looked around at animals, plants, all sorts of organisms, at humans, and they came to an astounding conclusion that all life on Earth has evolved by steady, modest changes and variants selected by natural selection, right? Now, they did not tell us what the mechanism of this change and this selection was. And Darwin had all sorts of hypotheses about this. But this big data resulted in a very important conclusion. And that's the key aspect of it, that, you could not have done this easily without big data, but you got a very pithy conclusion from big data, which was encapsulated in his book on the origin of species. And that book is an amazing book because that's an example of a scientific work which is written for the scientist, but also written for the lay reader. There is no popular version and there's no scientific version. There is just one version. and it's just extraordinary. Darwin didn't know the mechanisms of generating this variance, nor did he get into how variation comes from generation to generation in various organisms. In humans, for example, why do you look similar to your parents or your grandparents or not look similar and so on? The answer to that came from a small data scientist, Gregor Mendel. Gregor Mendel was working in his garden and he was looking at variation in plants, and he was getting into all sorts of trouble looking at quantitative traits. But then he homed in on the peas, and homed in on simple traits and looked at how they segregated and laid down the rules for how variation comes about from generation to generation. Those rules of segregation and assortment, again, didn't tell us what was inside the animal or the plant or the organism. That answer came from people who were both embryologists and became geneticists, like Thomas Hunt Morgan and others. Morgan and his colleagues saw the polytene chromosomes in the fruit fly Drosophila, and by X-rays, you could see physical changes in the orientation of the chromosomes. But that also correlated with characteristics of the flies which came out. And Morgan and his colleagues, Herman Muller, Sturtevant, and others, concluded that genes, which Mendel, Bateson had proposed when he, propagated, and others had proposed when they advertised Mendel's works, that genes were on chromosomes. So genes had a physical basis on chromosomes. There were others who were very worried at the time. Even Bateson was worried, because if genes were physically on chromosomes, in one generation, you saw a characteristic. In the next generation, that characteristic went away. And the generation after that, it came back. And this got Bateson extremely worried that, these characteristics were going and coming back, and perhaps there wasn't a physical basis for genetics. It was some sort of a mystical basis. But the fact that genes were on chromosomes and you can see this segregating changed that views rather dramatically. Of course, we know now about the structure of DNA. There's Morris Wilkins, Rosalind Franklin, Crick, and Wallace. And with the structure of DNA and how it could replicate to process information from generation to generation, we saw a fantastic link between how variation comes from generation to generation and how variation through evolutionary time causes changes. So this is the neo-Darwinian synthesis, which could give you the physical basis of evolution, as well as genetics, which could tell you what is the basis of variation. So this is, allowed us to understand nature's engineering in extraordinary ways. Now that understanding came about through our ability to use this brain which we have, which I alluded to, that is extraordinarily large and has cells which are propagated in number disproportionate to what other non-human primates have, other primates have. And their connectivity is like multiple supercomputers in parallel, right? And it's extraordinary what this brain can do. And this allowed us to not only make tools and change the environment and domesticate plants and animals, but it allows us to also, understand nature around us. That understanding has led to another source of big data, and that big data is the connectome in the brain. And this shows the connectome in one part of the brain of a model organism. If the brain is necessary and important for consciousness, movement, smell, taste, understanding how every neuron is connected should give you all the answers. Looking at the firing of every neuron upon stimulus should give you all the answers. So we've got enormous amount of big data in model organisms, in flies, worms, zebrafish, rats, mice, about connectivity and anatomy and function and physiology. But this has not told us proportionately enough about how the brain processes information. The language of the brain is still elusive in terms of how it is robust in many contexts, in other contexts not, and how it gives information. So there's a great need for a deep biology going into this. So today, what are the key questions we ask of data generated this way? Either neuronal connectivity, single cell RNA sequencing, or how many people have diabetes and how old they are, what is their weight, what is their height, what is their family background. from all of this, what are the key questions we ask of data? First of all, we ask, what is its provenance? Where does the data come from? Is it annotated? Is it done properly? What are the context and so on? Then we ask, what are correlations between the data and what is context? What is causal? And both these require us to be experts in the area. You cannot have a city transportation expert look at the data from diabetes and come to conclusions about what diabetes is about, or vice versa. It requires to have a deep training and understanding. Therefore, institutions such as NIMS, which analyze data, are precisely for that reason deeply connected with those institutions which generate data, and they work together, and only then you have this understanding. So what's happened is that technology has dramatically changed our access to data. The kinds of information we used to need to get, which took years, can now be literally got in an instant. People of my generation, when they did their PhD, got a PhD for sequencing one small ribosomal RNA gene, and they did that in 3 years, right? And they got a PhD from a top institute in Cambridge, from the Laboratory of Molecular Biology, actually, for doing that. Today, that kind of sequence can literally be done in an instant, right? And therefore, your job is not to sequence and generate the data, but to analyze the data. So access to data is given. So we need to dramatically change our ability to use it. And therefore, biologists have to become quantitative people with great speed. You cannot outsource that anymore. So how can data help us understand the universe better and apply our understanding in a better manner? Now, technology gives us access to data across scales, but is more better. From the nanoscale to the system, there are a huge number of examples of the success of big data. For example, if you want to look at data in radiology or in skin cancers, the massive collection of information allows computers to make diagnosis, which would have taken a long time. And therefore, pathologists now will need to go to a different level of analysis of the data than previously. So there are examples of success. But is it just that the low-hanging fruit has been picked? And now we're getting into more and more complicated demands on how to analyze data. And where do we go from here? Big data, of course, is very valuable. And people of a certain generation mourn its onslaught, and they're just wrong. Big data is absolutely necessary. It's here to stay. But Sidney Brenner, the famous biologist who died a few years ago, he made some very important points about big data. He said we're thirsting, well, before that, what he said about biologists is biologists ask 3 questions. They ask, where did it come from? That's evolution. How does it work? That's physiology. And how is it made? That's developmental biology. Medical doctors use these 3 learnings to fix things which are broke or prevent things from breaking. Engineers, of course, do something similar with science in other areas. But Brenner said that we are thirsting for some theoretical framework with which to understand big data. And this is the crying problem in biology. Over the last several decades, we have been constantly thinking that with more data, we'll get a better theoretical framework, such as is there in physics, and get a better view of predictive biology. When big data is analyzed in physics, it either proves or disproves a theory, or it actually opens up a new theory, which has extraordinary predictive value. That's not the nature of biology. More data doesn't always result in a new theory. It resulted in the case of Darwin's theory of evolution, but those are rare examples, right? So we are thirsting for some theoretical framework, and it's not clear how that will come. Although many believe that more is better, having more and more data tells you now, history tells us actually that least is best. That some of the great insights have come from using this data is necessary, right? But having deep insight into the physiology, the developmental biology, or the evolution. So we need theory and a firm grasp on the nature of objects we study to predict the rest. Now the question is, and this is the final point I'd like to make, what is that firm grasp on the nature of objects? People who study genetics genetics believe that by looking at sequences of DNA and the variations, they can understand, behavior. So they look at gene sequences and they look at behavior, or they look at gene sequences or they look at the brain. They look at gene sequences and they look at, the heart. People who think that we should look at gene expressions now have started looking at, RNA sequences and all of the above. Then others look at, mass spec data and put that together and look at all of the above. All of this is valuable, but at the key in biology is the cell. DNA is necessary because it connects all cells. RNA is necessary because it uses to communicate with DNA and make the properties of the cell. But understanding the cell, how it interacts with other cells to build tissues and when it breaks down what happens is the key. So cellular function is critically important, and that we must keep in mind is the center of our abstraction, and not about the data alone, which is necessary, which is important, but it will not be sufficient. So we have to become, top quality cell biologists and tissue biologists in, cardiology and liver biology or neuroscience and so on and so forth. Now, the conversion of data into knowledge is a great challenge for the future. Systems approaches claim to solve this problem, and deducing models of function from the behavior of a complex system is an inverse problem, which is theoretically impossible to solve. By looking at all the cards which are going around All India Institute in greater and greater and greater detail, you cannot predict what time someone is going to be leaving their homes and coming and going to work and doing something or the other, right? You can predict what's happening around over there. And the reason for that is there are many possible solutions to this prediction problem, right? The square root of 4 is 2, but the square root of 4 is also minus 2. And when you go to larger and larger sets of numbers, you get many possible solutions, but only a few or 1 or 2 will fit the actual context. And that requires, again, an understanding of people, who they are, how they go to work, where do they get started, and so on. That combined with the big data can be useful. So domain knowledge is going to be important as well. Now, you cannot easily escape also to higher level holistic approaches. People would say, I will go holistic and I will look at, people from outside, the brain and behavior, and I'll predict everything. Now, that doesn't work out in biology, because the essence of all biological systems is that they are encoded as molecular descriptors in their genes. So genes are important. You cannot escape from genes into holistic areas, and you cannot rely only on genes. And again, the cell becomes important. And since genes are molecules that exert their function through other molecules, the molecular explanation must constitute the core of understanding biological systems. So holistic escape is also not possible. Again, if you're a cardiologist, you know that these are the molecular systems which are involved in cardiac function and failure and so on. And you cannot just measure things without keeping those molecular parameters in mind. You can, of course, measure things. So I'll give you one last example and then I should stop. The point is that one can solve the forward problem of computing the behavior of the system from its components and their interactions. And big data is important here. But as I said, the correct level of abstraction is the cell. And this is illustrated in this photograph of this giant squid. And Hodgkin and Huxley took this giant neuron out of the squid. And what they did was they clamped the neuron, the voltage clamped it, or they current clamped it. And after voltage clamping, or they took out the insides and fixed the voltage difference between the outside and difference at a specific level, and then looked at how currents changed. And they did the other way around. They clamped the current and looked at how voltage changes. And by looking at the way parameters changed when they infused with different ions, they came up with the idea of ion channels and what those channels were, sodium channels and potassium channels, and what their role was in generating the action potential. It is a forward problem which they solved in an extraordinarily complex system. Now imagine you're here today and you say you don't know how the action potentials are created and function. And you took the neuron and you took out its cell body and you sequenced all the RNAs over there or you sequence all the proteins and you saw where they were localized, you wouldn't have a clue as to what's going on. You would find, there are hundreds of potential channels, and, the RNase coding for them would be there. And, you would have a tough time guessing at function. So unless you link that data with physiology, which you can do now in many contexts, you will not have an understanding. Unless you link that with evolution, just as, the channels which were isolated and identified in the squid, they are conserved from, worm to fly to human. That opened up the entire field of looking at potassium channels and diseases of channels, and all sorts of neurological disease and cardiac diseases. That evolutionary link was critically important, combined with that physiological link. And looking at how these channels are involved in making of the tissue, that was all important. So on these fundamental three questions, which biologists ask, where did it come from? How does it work? How is it made? That needs to be integrated into our questions of big data. There is lots more to say and do, but when you have a big challenge about big data, there's a simple point which Alan Turing made in 1950. We don't know what things will look like 10 years, 20 years, 30 years, 40 years from now. But he said that we can see only a short distance ahead, but we can see plenty there that needs to be done. So let's focus on doing the right thing now. And of course, 2050 will be a tough time, but as scientists, we should focus on what we understand and what we can do. And the final point is data we get from, say, imaging and microscopy is very important. But the critical point is what lies behind one eyepiece of a complex instrument can still matter. Thank you very much.
Thank you so much for that intellectual feast, as Professor Bhargava also mentioned. Thank you so much, sir. And also highlighting it in a simple language for us to understand that data is important, but understanding the context in which data is collected is also important, for not only predicting, but also for deciding or informing the policies and programs, so to say. Thank you so much, sir. Now, I request our Secretary DHR and DG ICMR to honor Professor Vijay Raghavan by presenting a memento. May I request Dr. Lucky Singh to kindly give it to me. May I request Dr. Vishnu to kindly.
Is it Oration award?
Yes, sir.
Momentum.
Yes, sir.
इसके साथ ही
I request Dr. Prof. P.P. Talwar to kindly join, sir. Please come in. And I request Professor P.P. Talwar to kindly felicitate Professor Vijay Raghavan by presenting a shawl. So Professor P.P. Talwar Oration Award also carries a cash award of ₹20,000. Professor Vijay Raghavan has donated this to the institute. Thank you so much, sir. As we come to the closure of the program, I now request Dr. Himanshu Chaturvedi. Sorry, sir. Yes, sorry. I'm extremely sorry.
Yes. So good evening, sir. Actually, our staff has prepared a kind of heavy about the institute because it happens to 46th Foundation Day also. So our staff, directed by Dr. Geeta, Dr. Saurav, Dr. Sarita, Dr. Tulsi, and I'm going to tell what Dr. Firoz has joined 1 week back, sir, the medical scientist B, the secretary has given to us. we has made within 1 week the whatever the AV, all the technology has prepared. I think you will give a tough competition to the IT people. Please. Yes, Jain.
The National Institute of Medical Statistics, ICMR-NIMS, is one of the premier institutes of ICMR. It was the vision of Dr. C. Gopalan, former Director General, ICMR, and Professor C.R. Rao, the legendary living mathematician and statistician, to set up an independent institute for research in medical statistics, IRMS. The IRMS grew under the leadership of Dr. A.D. Taskar, Professor Ramchandran, Dr. S.S. Verma, and Dr. Padam Singh. Many projects of national importance were designed, planned, and conducted here during their tenure. In 2007, during the directorship of Professor Arvind Pandey, IRMS was renamed the National Institute of Medical Statistics. Dr. Shukla was the director in charge from January to December 2017. Dr. M. Vishnu Rao, the present director, took over in December 2017. Under his leadership, ICMR-NIMS has diversified its research ambit from a hypothesis-driven approach to include a data-driven approach and big data analytics. ICMR-NIMS provides statistical expertise, undertakes methodological research, and conducts systematic reviews and meta-analysis. It has diversified in disease modeling and artificial intelligence. The institute is involved in planning and designing studies, conducting large-scale surveys and epidemiological studies. In addition, it has undertaken socio-behavioral research among tribals of central and northeastern states of the country. Capacity building workshops and summer training programs on research methodology and applied biostatistical methods are periodically conducted for students and researchers. With experienced scientists, the institute is supported by technical officers who help in field surveys, data management and analysis, and administrative staff. The institute has also awarded PhD in medical statistics. ICMR-NIMS has been designated as the nodal institute to estimate the HIV burden in India and all the states or union territories by the National AIDS Control Organization since 2003. ICMR-NIMS is also partnering agency for malaria estimation, NCD risk factor surveys and other vector-borne diseases by the Ministry of Health and Family Welfare. Data from nutrition, TB, maternal, and child health projects are analyzed using modern statistical techniques to inform policies and programs. The institute has also generated disease burden estimates at the national and state level. The Clinical Trials Registry of India, CTRI, is one of the major flagship programs of ICMR hosted at ICMR-NIMS. In 2007, it was established as one of the primary registries of WHO International Clinical Trials Registry platform by the former Director General of ICMR, Professor N.K. Ganguly. 36,000 trials have been registered to date from modern and alternative systems of medicine. Recently, a dedicated module for the data capture of Ayurvedic trials has been incorporated into CTRI, which was launched by the Honorable Minister of Ayush, Shri Kiran Rijiju. The National Data Quality Forum, NDQF, is a significant initiative of the Institute. As a multi-stakeholder collaborative platform, it strives to promote adherence to good practices for conducting demographic and nutritional surveys. Through educative webinars and outreach programs, the NDQF is a step towards improving the country's quality of demographic, nutrition, and health data. ICMR-NIMS was one of the response teams of ICMR during the COVID times. The National COVID Registry portal of ICMR is designed and hosted by ICMR-NIMS that provides clinical data of COVID patients from 53 hospitals across India. Research studies on the impact of COVID in the community and on the healthcare system have given valuable information to the scientific community. ICMR-NIMS initiated Professor P.P. Talwar's Oration in 2015, with the objective of highlighting the importance of program evaluation in the country. An eminent scientist is invited to deliver the oration. Professor M.K. Bhan, Professor M.S. Swaminathan, Professor N.K. Ganguly, and Professor Vinod K. Paul are previous recipients of this award. Through innovative analytics, artificial intelligence, and data management, ICMR and IMS strives to provide the best solution.
Thank you so much, sir. I mean, all of this is because of the continued support from the leadership and all the experts. Thank you so much for that. I now request Dr. Himanshu Chaturvedi, Senior Scientist, ICMR-NIMS, to propose vote of thanks.
Honorable Professor K. Vijayaraghavan, Principal Scientific Advisor, Government of India, Professor Balram Bhargavji, Secretary, Department of Research and DG ICMR, respected guests of ICMR, respected guests, Director of ICMR Institutes, and ICMR Head of the Division, and all my colleagues of NIMS, including who joined virtually online. It is my privilege to propose a vote of thanks on this special occasion of Professor P.P. Talwar Oration. I, on behalf of ICMR, National Institute of Medical Statistics, and organizing team, including director, and on my own behalf, I extend a very hearty vote of thanks to Professor K. Vijayaraghavan for his inspiring oration on big data and big ideas of discovery and application in life sciences. We were highly grateful to you, sir, for sharing your excellent ideas and multidimensional research approaches in the biological science to solve the major health issues and problems of our country. My sincere thanks to Professor Balram Bhargavji, Secretary DHR and DG ICMR, a great visionary, for his excellent guidance and support and regular encouragement provided to us, especially sparing his valuable time for this occasion. This is a wonderful occasion for all of us, and it is possible due to Professor P.P. Talwar. He is present with us to grace this occasion. I express my heartiest thanks for his presence and for sharing his excellent views. I also thank Professor Padam Singh for his guidance and regular advice and recognize this kind of activity or need any help. I extremely thankful to you, sir. I must mention our deep sense of appreciation to all the guests. Professor Arvind Pandey, ex-director, who was available with us online, and Dr. D.K. Sukla, ex-director in charge, Niranjan, and many more people. I could not name everyone, but I appreciate that they could find time to present with us on such a important occasion. I'm also very grateful to Mr. Dr. M. Vishnuvardhan Rao, Director NIMS, and organizing team of NIMS, as well as ICMR. In fact, ICMR has extended its maximum support for this activity. In fact, its preparation was started about 6 months back after the search committee meeting, and it continues almost every week, some or other activities. And I would also like to acknowledge our gratitude to head of the division of ICMR, senior scientist, senior DDG, FA, and faculty of AIMS and other organizations who have joined us either physically or online. I'm thankful for the support and services provided by ICMR and NIMS staff, including administration, in organizing these important activities. Sir, we are inspired by your great words of valuable suggestions. And sorry if I have missed anyone. Thank you all.
Thank you all for your kind attention. Request those who are present in person to kindly join us for the high tea served in the canteen. Yeah. Thank you.
Yeah, you'll get that. You'll get
First time देखे तो बहुत अच्छा लगा।